Well, I'm happy to be here. This is the first time I've been to this region of the world. I've never been to the Balkans before. And though I'm happy to share, I'm actually more interested in feedback you may have on this concept. This concept has been already implemented, at least partially implemented, in a number of different countries for two different sectors, government and also for public health. But this approach is something that we quasi-stumbled across as we were trying to solve some very specific and unique interoperability problems. So the topic here is how do we enable knowledge sharing by maintaining links between independently developed spatial knowledge graphs. So the United Nations Committee of Experts on Global Geospatial Information Management wrote a white paper in July of last year stating that data, even though it's critical, is no longer valuable as a standalone entity because we have changing user expectations, we have a widening geospatial ecosystem, the people who are interested in geospatial data are no longer the GIS practitioners, and we need to move away from data-centric to more knowledge-sharing infrastructures. So a lot of countries have implemented a national spatial data infrastructure, and they need to move to a more knowledge-sharing infrastructure. Knowledge sharing is very important because there are a lot of problems and challenges facing the planet and facing humanity. Environmental is an obvious one, public health, economic. In order to address these, there needs to be a lot more institutional collaboration between federal, local, and tribal governments, the private sector, and nonprofits, and institutions of education. But how do we collaborate with knowledge versus just data, especially because the tools that we all have been using come from a legacy of data management, not necessarily knowledge management. So tabular data sets do not necessarily encapsulate semantic properties. Two dots on a map don't necessarily tell us if we were dealing with the same location or potentially two locations, and there's margin of error there that's creating some ambiguity when it comes to semantic identity. So spatial knowledge graphs are an ideal representation for reasoning because they can model large networks of features, they can model semantic properties. Now in this talk, we're going to be talking about labeled property graphs versus RDFs and triples. So a labeled property graph, you guys may be familiar with the graph database Neo4j, and especially if you're familiar with ArcGIS knowledge, Neo4j is the graph database that's actually being used underneath the hood. So in a labeled property graph, you have objects, you have nodes in a graph that represent objects and their state. And so that's really what labeled property graphs are best for, is modeling state. Triples are a lot more flexible, so if you're trying to do different kinds of analysis that don't require schema changes, then that's what they're best suited for. But for this talk, we're going to be talking about labeled property graphs, specifically because we're trying to keep track of state of geographic objects as they change over time. So yeah, in order to facilitate this interoperability, we need to have some sort of semantic standard within an ecosystem. Now the terminology we're going to use here, two new terms. Geo-object is a feature within the context of a spatial knowledge graph. So in a knowledge graph, you'll have a node, and the nodes represent locations, and we refer to those as geo-objects. And then a geo-object type is sort of the schema definition of that geo-object. So a lot of governments, a lot of institutions are working more toward FAIR, that is findable, accessible, interoperable, and reusable. But when it comes to knowledge sharing, there are a lot of challenges. Now again, we're not talking about data catalogs, we're talking about actually facilitating the sharing and exchange and interoperability of knowledge. So one thing that graphs are really, what makes them ideal for sharing knowledge is they're focused more on the individual location versus the data set. So as a data catalog might share a table, a spatial table, or it might share a layer. That's more data set centric. But with a knowledge graph, you can answer questions like, show me everything related to this particular location. And ideally, which we'll get into the temporal piece in a bit, for what period of time. So when it comes to findability, it's not easy to say, show me everything associated with this lake bed, or this levee, or this recreational area. That data tends to be distributed across a number of different silos, and that's not something that information is not easily findable. Also, there are accessibility challenges in that a lot of spatial knowledge graphs are developed for internal or analytics purposes only. Right now, I'm making a generalization here, but spatial knowledge graphs that are very granular and cohesive tend not to be treated as first order objects, so they're not necessarily easy to find. Interoperable in the sense that you can't necessarily establish semantic identity between locations, so you might have okay, let me put it this way. There are certain graphs that are well known even in academia where even within them you have the same location represented twice because those locations came from different data sources and there wasn't a way to establish semantic identity. So you actually have silos within the single graph. And then reusable in the sense that in an ideal world, if someone publishes a graph, let's say on hydrography, and I'm into transportation, I should be able to import that graph. Everything should line up by location, and then I can start asking queries like, show me what transportation infrastructure might be affected by flooding. So this is the pattern that we're introducing here. It's called a spatial knowledge mesh. And I'm very curious to hear what you guys think about that label, because it's a specialization of the data mesh pattern. So a data mesh is designed to overcome the shortcomings of a centrally managed IT solution. So data mesh is much more distributed, and rather than having a single IT team managing data from multiple different domains that they know very little to nothing about, the idea is that the domain experts publish the results of their data as first order products that then people can directly subscribe to, but you need some kind of interoperability layer to make sure it's compatible. So in a spatial knowledge mesh, you need to preserve the authoritativeness of data. So speaking, having worked with US agencies and bureaus, and this is a problem that's common everywhere, people copy each other's data, but is it authoritative? Like if you are going to a data catalog or you're going to some other portal, is that data authoritative? That authoritativeness needs to be preserved in the metadata as data are being copied from one place to another. So you have this notion of an authoritative copy. This is the temporal piece is something that's typically also lacking. So I'm looking at a data set, but for when was it valid? Not when was it updated, but for when were these values supposed to be true? So am I looking at data that's valid from 2010 to 2015? What is it? That needs to be captured in the metadata in a machine-readable way. And then it should be distributed, and that's where we leverage the data mesh pattern. It is a lot of overhead to expect any organization to build semantic models by going independently and building their own data pipelines to all these different organizations, bringing in their data. Rather, people should be able to subscribe to the published knowledge graphs they're interested in. And also importantly, versioned. What version of the data am I leveraging? So as new versions are being published from a machine-readable way, I should be aware of that and then in a controlled fashion be able to leverage the newer version. Also, a very important part of this pattern is the transitive property. So here we have three organizations. Organization A has created a spatial knowledge graph that's leveraged by organization B. So there's a dependency here. So organization B is green, but then organization C has a dependency in organization B. By virtue of the fact that they're subscribing to organization B, they should transitively inherit everything that's published from organization A. So the idea is as organization A independently publishes new versions of their data, that is immediately known to organization C. They're not necessarily bound to organization B updating their published graph. Also, they should be interoperable by common geographies, by common locations. So again, I should have clarified earlier, so in these spatial knowledge graphs, these nodes are locations. And then the edges represent a spatial semantic property that captures an edge. It can be located in, it could be downstream from, it could be adjacent to. It really depends on the nature of the domain. So in this example, organization B and C have a dependency on A. Now, if organization D subscribes to B and C, then there should not be 2 copies of A. There should be 1 copy of A. Now, where you may potentially have a mismatch is organization B may be leveraging organization A from T0 from some point in time. Organization C may be referencing organization's A data from T1. So there might be a temporal mismatch, but at least from a semantic identity standpoint, we shouldn't have multiple copies of the same location in a graph unless it's a different abstraction for an entirely different purpose. So this is just sort of an overview of how the pattern works, is that organization A will publish their knowledge graph. Once they have vetted it, they treat it as a product and they publish it for a certain period of time, then other organizations should be able to subscribe to that and pull it into theirs. And what we found out that as we were implementing a version of this, specifically for hierarchy management, starting in developing countries in a disease intervention context, the problem there we were solving is that the Ministry of Health has a master facility list of facilities that references the administrative hierarchy, yet the administrative hierarchy is managed by a different ministry and it's always changing. So how do we automate the propagation of change in that context? And we'll get into that in a little bit more detail. And so what we realized what we were building is we were building this notion of a graph repository. It's very similar to a code repository in that it's maintaining and managing dependencies between graphs managed by other organizations and keeping track of the temporal component. And this notion of a common geo-registry is the semantic interoperability when it comes to location. Terminology service, we won't touch a whole lot on that. So, a common geo-registry provides a single source of truth for managing geographic data across time from the organizations with authoritative mandate. So a CGR is what says this data is authoritative because it comes from this ministry or it comes from this organization. It manages the temporal piece. What is the periods of validity for different the attributes, for the geometries, and for the relationships between other geo objects. And as a result, it's able to manage the versioning and interoperable piece. Data mesh, we already kind of talked about this, but the data mesh pattern is what allows us to operate in a more distributed environment. So back to here, just like a code repository with GitHub. I know in the old code repository days there was this notion of a central code repository, but in GitHub everything is a branch, and that's the same concept here. Is there is no centrally managed repository. Rather, the organizations build custom fit for purpose graphs, leveraging the information or the knowledge that they need. So this notion of a knowledge graph repository also manages the temporal aspect, distributed and versioned. So our implementation is called GeoPrism Registry. It's open source, and it's the first implementation of this Common Geo-Registry concept. Now, a very important aspect of a Common Geo-Registry is that it manages locations or geo-objects' identity, classification, geometry, relationships to other geo-objects, and what we call historical events, splits, merges, and combined, for the correct period of time. And that's it. The goal of a CGR is not to be just a geospatial data warehouse. So the idea is that if a CGR is managing an administrative hierarchy for a country, that you don't have domain-specific attributes on there like population, because population means different things. In a public health context, actually there are multiple types of population are used in public health. From a taxation purpose or perspective, you have a different population numbers, but the idea is that it is domain agnostic other than just focusing on just these properties, and this is the focus of our work, is facilitating interoperability by location. It's being used by the Ministry of Health in the Republic of Laos, National Geospatial Agency in Mozambique for facilitating cross-sectoral collaboration by these common geographies. And more recently, we've started to deploy it for U.S. Forest Service in the context of GeoPlatform.gov. So this is a little bit background, and I apologize. I think this is kind of hard to read based on the resolution. So basically, what we have here is this is the original problem we set out to solve, is in public health, you have an administrative hierarchy from some organization like the Ministry of Interior. Then within MOH, it stands for Ministry of Health, they have multiple different hierarchies. They may have a geographic hierarchy that references the administrative hierarchy. But a common problem is as boundaries are splitting, merging, changing over time, the facility list for the Ministry of Health is often out of date. And other types of hierarchies that include things like villages that they directly use for planning, if those are stale, then when it comes to disease intervention and planning campaigns, those entire villages can just get overlooked. And so that's why this notion of a Common Geo-Registry is now a concept being promoted by the World Health Organization in their micro-planning and GNS-enabled handbook. So this is an example of the graph repository as implemented within GeoPrism. This is how we manage those dependencies. We keep track of the authoritativeness of each node, their relationships, and how they relate to each other. And what's not captured in this diagram is the temporal component. So as changes are being made to graphs that are referenced by other graphs, and this is all kind of defined in metadata, that those changes can automatically propagate for the correct period of time. And so here's just, and probably not very readable, but here is the API for defining these different types of runtime. So, I mean, obviously there's a UI component, but there's an API for you can define new GeoObject types, new hierarchy types. You can define directed acyclical graphs and undirected graphs. So you can define these types within GeoPrism at runtime. And of course, obviously, instance data can be defined through a RESTful API as well. And this is, for those who are interested, this is the so what I showed here before, that's sort of the facade of the metamodel, but internally, this is the abstraction we used where we can create, allows the definition of new types of graphs, new types of edges, new types of classes, because also what we initially set out to do is what we publish for certain periods of time, we added support for publishing those as tabular data sets. So the idea is if people want to create a tabular view of what the graph looked like and which relationships in the graph for different periods of time, that's something we support because we live in a world that's still dominated by tabular data structures. So when it comes to the time management component, we have this notion of period of validity. So I don't know if this is readable, but over here on the left, we're looking at inside the graph. So we're using OrientDB as the graph database because it supports a document model. And it's also a really good permissive open source license, is that we can store the change. Here we're focusing on attributes, so we can store the change of these attributes over time. And again, it's not when they were updated, but it's when they were valid. And we also make the distinction of saying we know what the value was for something in 2010 as we understood it then, but we also can keep track of what we know that value was in 2010 today, because the value that was specified in the past was an error, but we need to preserve that historic snapshot because operational decisions were made off of that. But then when a graph or a table is published, so a published product, you specify the period of validity, which is for which value and what is the period for which it is valid as far as the outside world is concerned. Because internally there may have been some changes, but that may not be relevant to external parties. Okay, I got to hurry through this so we have time for questions. But here's what the graph repository looks like when it comes to managing relationships. So here is a hierarchy for U.S. Forest Service, and the time component is kept track on these different edges here, and in the center we have a combines event. So we're keeping track of saying Forest 2 combined with Forest 1 at T2, and at T2 District 3, because its parent merged with another, then has a new parent. And so that allows us to publish these label property graphs for these different periods of validity, which can then be referenced by other organizations. And in this case, it's a drone data management app that we built for the U.S. Department of Interior. So to wrap this up, future work is that I'm leading a session at the Earth Science Information Partners meeting next month. And the goal there is to get more knowledge sharing use cases, to get more feedback on the approach. Some other things we've identified that would be useful is to implement support for this notion of symbolic links between graphs. So as we start to implement merges, the idea is some of these graphs get really big. Should we really copy the entire graph that we're referencing? Because that could result in a lot of duplication of storage. Instead, let's just copy symbolic links to minimize storage costs. And then the idea of publishing to RDF triples as products would be very interesting. How do we formalize that mapping between labeled property graph and triples? But ultimately, we need more test cases to demonstrate whether this approach actually lowers the time required to share knowledgeable products between different organizations. I'll leave it up to questions now.